Yeah, hello. I'm very honored and very happy to introduce this afternoon session here. So I have been very nicely introduced. I'm just a deputy, and I see many people here are from EuPRAXIA. So maybe the things I'm going to say in the 14 minutes that are leaving are probably things you already heard and slides you have already seen. So I'm just the deputy. Don't shoot me, since we're in the city of music. So yes, right at the beginning. So you know, who are in EuPRAXIA, and those who are not have probably heard about. This is a collaboration of 40 institutes. It's European centered, but the scope is going much beyond Europe because it's also taking in associated partners from East Asia and from the United States. So these red dots, however, are most concentrated in Europe. And this is a big European endeavor for planning to propose the first dedicated laser plasma accelerator for research and for applications. So it's not about laser experiments, it's not about laser acceleration experiment, and maybe it's about plasma accelerators and not experiments at all. So what I wanted to say is particle physicists, accelerator physicists, they're people who really like to look far in the future because investments that are needed for the instruments of their research are necessary to have a far future look. And the question is that we see that accelerators become bigger and bigger, and because they're becoming bigger, the cost increases. And the question that you could ask, can we overcome the limits in size and cost? Wouldn't it be great to build particle accelerators much smaller and more cost effective? So probably this morning, the cost effectiveness is not something which directly appealed to the young audience that we had here, but I'm sure that many people here who are adult and taxpayers are very much in favor of doing better science with less investment. So cost effectiveness through reduction of size. What would this bring us? It could, of course, help us to push back the energy frontier, which is now set actually by the LHC in Geneva. And if we want to go forward, it's only one way, it's pushing back the energy frontier for new discoveries. It could help us to develop free electron lasers that are available and affordable for more institutes, for university institutes, maybe in basements of universities. And there's a strong demand for free electron lasers for applied science, life science, material science, space engineering, you name it. One can dream about cost-effective electron irradiation therapy facilities. One could even think about accelerators that are so small that you can put them into the human body, or that are so light that you can put them in outer space or on other planets. But maybe these are all very valuable roads to go. But one important point is to have compact irradiation facilities for diagnostics, inspection in medicine and industry. And this is something that is very interesting and could be addressed with this endeavor. So why is this interest in laser plasma acceleration so strong? Why is this interest in plasma acceleration at all so strong? Because it's not only about lasers. It has all come, let's say, a decade and a half ago, because something people imagine sprang into life. It's the internal injection in laser plasma acceleration. That is why I always mention lasers here. And the phenomenon is, most of all, you are familiar with this. You just shoot a very intense laser beam. That means high power concentrated on a very small surface. This is intensity, into a completely ionized gas. The laser does this if it's not already ionized, and expels all the electrons from a region. The ions remain there and create an electrostatic field. And those who remember Electrostatics 101, they remember that there's an electric field pointing to the center. And the miracle is that plasma electrons get trapped in this bubble and then get accelerated. And they get accelerated at kinetic energy increase rate per length, which we call gradient, of 100 gigaelectron per meter, up to 100 gigaelectron per meter. And this is 3 orders of magnitude roughly above what conventional accelerators can do at present. So this was a big promise. And since then, the dreams that I just listed in my previous slide, we can now feel allowed to dream those dreams. By the way, this accelerator fits into the size of a human hair. 25 microns, typically this is the spot size, and the bubble is very short and it propagates over distances of, let's say, 100 or of tens of centimeters to get to these energies, to high energies. So, of course, I don't mention the size of the lasers is behind, so this is a little bit over-exaggerating, putting it in human hair, but the accelerating structure is very small. So, if one compares on this plot the size of accelerators versus energy, and the size in meters on a logarithmic scale, so every step from here to here is a factor of 10 on a double logarithmic scale versus energy, and these points here are linear electron or positron accelerators, mainly driving light sources, free electron lasers, not all of them, like SLAC, but many of them, Swiss Fell, for example, LCLS, SACLA, and so on. And you compare the experiments that have been done on high-power lasers to accelerate electrons, you see that the energies that have been reached successively come into the GeV range and with lasers, and even beyond with beam-driven accelerators, which I will just mention at the end. But you see this higher acceleration rate per unit length, which means the gradient is 3 orders of magnitude higher. So why don't we have already accelerators based on this technique? The reason is the issue of beam quality. These have very high quality beams of the quality that is required for light sources, for example, very, very demanding applications. Whereas these accelerators, these acceleration experiments have beam qualities that are not so good. And how do we assess beam qualities? There are many ways to assess beam qualities, but let's say the most important parameter, and this has become apparent in the discussion that we just in our collaboration meeting in the last 2 days, is that the energy spread is a very important factor. So the energy spread, what would you mean by this, is that all the energies that are produced in an accelerator and accelerated at the output of the accelerator don't have exactly the same energy. There's a little straggling of energy ranges around a mean energy, and this tends to be in the few percent range in laser plasma acceleration experiments, which are shown here. You see this is 1 and 10% range of the relative variation of beam energy between the electrons in the beam, whereas what is necessary, for example, in demanding applications like light sources, is in the per mil region. And this is what EuPRAXIA aims at, putting into existence plasma accelerators that address the quality problem, so that we can really talk about something which becomes concurrential here at a smaller size, at least of the accelerator. So we want to get there. Why? Because we see that there are many applications that can be addressed here. High energy physics, of course, will be one client, but accelerator R&D, trying out these techniques and perfectioning them, is very important. But photon science applied to material science, medical and life science, not only medical but only biology and structural molecular chemistry, as we heard this morning, are very interesting applications, and also for the industry. So this on this honeycomb graph are shown here, and these are really put into the center. Trying to design a facility that can deliver beams that are of reliable quality is also an obligation to go towards this road, yeah, and having something ready at the end, yeah, beyond just demonstration and first demonstration experiments. So I have been talking about lasers. So one way to, one can ask, can a facility really do all of this? And there's one advantage to laser accelerators, that a laser you can easily switch around. And the plasma accelerator in itself is a very simple object. It has been shown in the talk by Ralf Assmann this morning for those who were present. It's a small cell of gas generally, or a plasma discharge, a not very expensive object. And can be multiplied. The expensive object is the energy supplier, which is in this case the laser, and can be easily switched around. So you can have easily many user areas, whereas in conventional application-oriented accelerator facilities, each beamline is a certain effort to construct. So I have been talking about lasers. I should also mention that there is this EuPRAXIA facility design is under design. So this is something how it could look. It's an artist's view with the laser systems here powering the drive lasers and an electron injector to provide the electrons. And a beamline that delivers the electrons to, for example, the applications, for example, the main application, the free electron laser. I should mention also that using lasers is not the only way you can do it, and it has been proposed at the same time in the late 70s, where people were thinking about laser plasma acceleration, also to use electrons. The physics behind, the plasma physics behind, is pretty much the same, and this has been demonstrated, as I said, over a decade ago with both, because with both techniques driving either putting the energy into the plasma waves through a laser or through a strongly focused and strongly longitudinally compressed electron beam, the only thing you need is something which provides the electric field to expel the electrons. And there is a design in National Laboratory of Frascati in Italy about using a conventional LINAC to drive a plasma wakefield accelerator and inject this in accelerated beam to the FEL. And the fabulous thing in EuPRAXIA is that we all can right now explore for our design these different approaches, because we don't know yet what works best. Yeah? Because for knowing what works best, you have to try it out. And this is the aim of our collaboration. So having said these words, I would like now just to give an overview of the afternoon talk, because the four speakers that have kindly accepted to present talks at this afternoon will talk about subjects that are all of vital importance for EuPRAXIA. Peter McIntosh, who is the technical director of the Accelerator Science and Technology Center in Daresbury, right around the corner, more or less, will talk about the industry opportunities in accelerator facilities. I mentioned industry several times, and we will hear very interesting things. I mentioned laser, and Cristina Hernandez-Gomez from the Central Laser Facility in Rutherford Appleton Labs will talk about the laser technology in 2025. And why we're talking about a, let's say, 5-year horizon is that's the horizon where we want to see EuPRAXIA starting to operate. By that, we are interested in the laser technology that will be available and reliably available at this time scale. So this will be very interesting. And of course, we expect not only big industry to be interested in EuPRAXIA, but also startups. And so we have a representative of the French startup company, SourceLab, Paul Dumont, who will talk about an application for X-ray radiography. And the last point is something which is very important, will be presented by Dr. Georg Korn, who is a director of ELI Beamlines, and will talk about the integration of a large-scale infrastructure, as EuPRAXIA will be. So I thank you very much for your attention, and I'm handing now over the microphone to Peter McIntosh.